Welcome. You are viewing one of 10 modules developed through a project funded by Geoscience BC focused on direct-use geothermal resources in British Columbia. This follow-up project was carried out between August and December 2016. The project was executed by Geothermal Corp. These modules were developed from the Direct-Use Geothermal Resources Roadmap published by Geoscience BC in June 2016. They incorporate additional educational material that were developed as part of the current follow-up project. The voices you will hear narrating the module are myself, Catherine Hickson, and my colleague,
Juliana Proenza.
Welcome to Module 2 of Direct Use Geothermal Resources in British Columbia, Canada. So today we're going to talk about what is, where is, and why geothermal. As an overview, we're going to start with what is geothermal, and we're going to look at the spectrum from power generation down to what's called geoexchange. Then we're going to look at where it's found globally, and then why are we interested in geothermal? Why is it important to Canadians? So geothermal energy has been used for, well, probably as long as humans have been on Earth, because hot springs, sources of warm water at the surface, were very important for Indigenous nations. People would use this water for bathing, medicinal purposes in some cases, because it was handy, it was easy, and it was already heated. So you didn't have the significant amount of work that was required to heat up a large volume of water. Power generation is newer. That's been happening in the last 100 years or so. And it started in Larderello in Italy in the Tuscany region, which has a very large geothermal resource. Geothermal heat pumps, that we'll talk in more detail about later, started in the 1940s, but have had increasingly significant use since that time. So as we move, because what's important for power generation or direct use or geothermal heat pumps is the range of temperatures over which these various technologies can be applied. At the lower end, you have things like heating of buildings, we have drying of food, up to power generations. And that's what the diagram on the right-hand side gives you some idea in terms of what you can use all of this energy for. And what you see here that is important is that at the power generation needs to be about, at least 200 degrees Fahrenheit or above 95 degrees centigrade. Below that temperature, really, it can't be used efficiently for power generations. However, there are a couple of exceptions to that, which we'll talk about in later modules. So, what do we need to have a geothermal system? Well, the system itself is composed of the fractures that provide pathways to get groundwater, particularly rainwater, down deep to the point where they can be heated up by Earth's naturally occurring geothermal energy. And that geothermal energy has come over the eons by the breakdown of various radioactive elements, and in that process it produces heat, and that heat is trapped within the Earth. What we can do to get that heat is use a fluid like water to essentially go down to the point where the rocks are warmer. That water is then heated up and then can be extracted. So important to this are the faults and the fractures that carry the water. And if the water is brought back up to the surface fast enough, we will see it manifested in hot springs and geysers and fumaroles. So here's a simplified diagram. On mountains or hills around our valley, we have rainwater falling. That rainwater permeates through the rocks from faults and fractures. And the difference between a fault and a fracture is simply a fault has moved, where a fracture is a broken piece of rock. The the faults and fractures lead that water downward through an aquifer, and that aquifer needs to have some permeability to it, and then conducting heat from below, and that might be from a magmatic intrusion deep down the earth. So the cooling of that, the intrusion and then the cooling creates a wave of heat, and that heat is then dissipated and picked up by circulating groundwater, which can then be drilled and tapped. So geothermal energy is divided into kind of sort of large categories, and those categories really reflect how it is in fact used. So at the low to moderate temperature end, and that's been the focus of the project that we're undertaking now, at that low to moderate end, what we're looking at is these are temperatures which are not particularly good for power generation, and that's simply because the energy efficiency at low temperatures is not great with today's technology. But it should be noted that a number of companies are looking at better ways, more efficient ways to generate electricity from lower temperature resource. But for now, let's look upon that lower temperature resource for things like spas and pools, could be used for drying of vegetables or lumber drying. And it has been used in its natural form by local people, indigenous people, for millennia. Now, the moderate to high temperature, this is more localized and focused around volcanic areas in principle. In volcanic areas, we have magma, liquid rock, being brought up close to the Earth's surface, so it provides a direct source of heat at shallow Earth surfaces. And what we're talking about there is we're talking about heat brought up to a point where it can be easily harvested by today's technology. And today's technology is the ability to drill several kilometers deep at relatively low cost. So these are the resources which are the focus for power generation. And wherever you have volcanoes, you have the potential to produce geothermal power. And as noted earlier, this is a mature technology. It's been around over 100 years, and a lot of experience has been gained in many countries around the world to extract the fluid, or brine, just basically water that is filled with dissolved solids, and that dissolved solids come from the rock through which the water has been transported and dissolved because of the high temperatures. So that material we refer to as a brine. Now, geoexchange is a little bit different. Geoexchange is not extracting warm water directly from the earth, but in fact uses the ability of the earth to store heat. We'll be talking more about geoexchange in Module 3. Now, there are a number of other types of geothermal energy, but the one I want to focus on is hot dry rock, or enhanced or engineered geothermal systems. These hot dry rock systems are in areas where there isn't a fluid. We don't have an aquifer where water is moving through the substrate deep down underground, but rather we have hot rock. So what has been done at an experimental level in a number of places around the world is drilling into that hot dry rock, then creating a series of fractures around the wellbore, pumping down water, and that water is then used to harvest the the heat from the surrounding rock. A second well is usually then drilled, and it is that second well that is used to extract that now hot water. These kinds of systems are very important for the future, and they're important because there are many, many areas on the Earth where there is no volcanic activity close by. We have what are called crystalline basement rocks, and these are granites and high-grade metamorphic rock that have very little permeability, but yet in many cases are hot, or hotter than the average rock. And remember, as I mentioned, the deeper you drill, the hotter it gets. So as drilling technology improves and we can drill deep down into the subsurface, as we drill down deep into the subsurface, we can extract all of that heat energy. So EGS has the potential to be a source of heat energy in many places of the world, many more places, in fact, than we can get either power generation or direct use geothermal. So let's look a little closer at the temperature range and the possible applications. So the low temperatures are considered to be lower than 90 degrees C. And at low temperatures, there is not a good potential to produce power, but there's still a lot of heat energy in that fluid, and it can be used for such things as snow melting or space heating, swimming pools, because that's much higher. 90 degrees is much higher than you would normally heat a pool, for example. So even lower temperatures can be usefully used in many types of situations. For moderate temperature, we're starting to get into the range where we can produce power by binary means, and we'll talk about that in a couple more slides. At the high temperature end, we can efficiently use this brine for power generation. And power generation can be in a couple of different ways. One is dry steam, and the other is where we have both steam and a fluid or a brine that's produced. So really it is the spectrum of geothermal energy that is important. Everything from power generation to the storage of heat in the ground and extraction of it later through heat pump technology. And this GeoExchange is going to be the focus of Module 3, because in GeoExchange we're able to use that heat, we're able to use the capacity of the soil to store energy virtually anywhere. But it is only in specific locations where we have hot enough subsurface water temperatures to be able to extract them and use them for either direct use, and even fewer places where we're able to extract temperatures that are high enough to create power. Now, in terms of how we go about doing a project, is we have a lot of pieces that we need to deal with. And those pieces are how we go about creating a project. So we have our project, our geothermal project developers. So we have people who want to produce a project. And what you see in all of the boxes here are all the things that have to happen, whether or not we're talking about ground source heat pumps or we're talking about power production. And some of those things, so in the green boxes, you see specific things below the diagram. You see permits and access. That's important no matter how and what you're doing, whether it be low temperature geoexchange, just shallow subsurface, or you're deep drilling 2 or 3 kilometers to get power. Then we need to understand, once we have access to the ground, is what kind of geology is there. We may need to do some geophysics to understand our reservoir better. And then in that process, we need to explore and interpret. Once we've done that, we have a much better understanding of what does our reservoir look like? What do we need to do in order to exploit it? And we also will have an idea of what the temperatures are. So we'll be able to decide, are we doing something that is going to end up with electrical generation, or are the temperatures not sufficient for electrical generation, but we could say heat up a greenhouse, direct use, or are we doing something at an even lower temperature, which is using ground-based heat pumps? Now, the other thing to notice about this diagram, in addition to having a lot of different factors in here, is that as we move across and to the right-hand side of the diagram, it becomes much more costly. So financing is another part of the project development phase that is important to consider. So let's talk about what geothermal is. Now, we've talked about it as being the naturally occurring heat of the subsurface of the Earth itself, and we are able to extract that heat by drilling down to areas that have fluids, liquids, brines that are circulating, and essentially scouring or harvesting that heat. In the wells, what we're doing is drilling deep down and tapping that heat source. In the case of a binary system, so that's the lower right-hand diagram, a binary system, the heat that we're able to extract is not sufficient to run the turbine directly. But in fact, that turbine is run by heating a secondary fluid which has a much lower boiling point than water itself. Sometimes that's pentane, sometimes it's ammonia. It depends on the particular type of plant that has been built. For most systems, and most systems fall into that flash steam power plant, and in that type of system, the water is hot enough that it will flash. So we drill down deep, and by deep, I mean maybe it's a kilometer, maybe it's 2, maybe it's 3. We're drilling down deep. We're bringing that fluid to the surface at high enough temperatures that it flashes. And it will flash into a steam phase and then into a brine or a water phase. That water phase is then re-injected down into the reservoir. And that helps maintain the reservoir, its health over the long term, because we're not sucking out all of the water that is in that reservoir. So we bring the hot water to the surface, we flash it, the steam then goes through the power plant, spinning the turbine and generating power. And all of the condensed steam, as well as that separated water, are then pumped down back into our reservoir. In some cases, the steam is at a very high temperature, and it's called dry steam. And this means that when it's brought to the surface, there isn't any separated water that needs to be pumped back into the reservoir. The steam is simply brought to the surface, run through a power plant, and then the condensed steam is then pumped back down into the subsurface. This is, in California, in the geysers, one of the most important geothermal resource areas. The resource there is dry steam. And in fact, it is this that is going to be the focus of this little video that you're going to see. And in the video, basically, it's going to cover all of these kinds of geothermal power, with the exception of GeoExchange. You're going to see some pictures from California of the geysers area, which is the dry steam power plant, but you're also going to see pictures of the binary as well as flash steam power plants. So enjoy. The video is only about 3 to 4 minutes in length.
You may have relaxed in a natural hot springs pool, or seen the old faithful geyser blasting hot water into the air in Yellowstone National Park. But have you ever thought of where all that heat comes from? Well, it comes from deep beneath the surface of the Earth, and it's called geothermal energy. And we can use it to generate clean, renewable electricity. Okay, here's how geothermal works. Heat from the Earth's crust warms water that has seeped into underground reservoirs. In some places, when water becomes hot enough, it can break through the Earth's surface as steam or hot water. This usually happens where the Earth's crust, or plates, meet and shift. In the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural, renewable energy sources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. Have a look at this. It's a dry steam geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Pretty straightforward. Another geothermal technology is called a flash steam power plant. A pump pushes hot fluid into a tank at the surface, where it cools. As it cools, the fluid flashes, or quickly turns into vapor. The vapor then drives a turbine and powers a generator. A binary cycle plant works differently. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator. The environmental benefits of this clean, round-the-clock, renewable energy source are substantial. Low emissions, small physical footprint, and minimal environmental impact. The few byproducts that can come up are often re-injected underground. Geothermal energy can also help recycle wastewater. In California, wastewater from the city of Santa Rosa is injected into the ground to generate more geothermal energy. Some plants do produce solid waste, but that solid waste may contain minerals that we can remove and sell, which lowers the cost of this energy source. The U.S. Geological Survey estimates that untapped geothermal resources in the United States, if developed, could supply the equivalent of 10% of today's energy needs and cut our dependence on fossil fuels. In fact, electricity generated by geothermal energy already provides about 60% of the power along the Northern California coast, from the Golden Gate Bridge to the Oregon state line. Geothermal energy, helping to push America toward energy independence and a clean, renewable way to meet our growing energy demands.
So Kathy started taking you through the geothermal spectrum, starting with power, and we're going to move on now to direct use and geoexchange. So with direct use and geoexchange, you are essentially extracting heat from the earth for heating and in some cases cooling applications. And these applications can be used at the residential level. It can also be used at a higher density residential or commercial level, as well as industry, or things like greenhouses, lumber drying, vegetable drying, basically any process that requires heat. So what we've got here is we are looking at several different configurations in this slide as an example, where you are extracting heat through various forms, and that could be using horizontal coils, as in this example, and here, a horizontal closed loop, boreholes where you're drilling vertically, but not very deep in this case. So that's the important thing to remember about geoexchange, is that it is using shallow heat from the ground, basically anywhere from 10 to maybe even up to 70 or 100 meters deep in some cases. But then you've got examples where you're going deeper into aquifers that may be 500, 700, or 1,000 meters below the ground. And in that case, what you're doing is essentially using direct use. So if you're tapping into an aquifer, you're usually utilizing that water. In other examples, you're also actually exchanging heat from the ground at that depth through a downhole heat exchanger, and then you are utilizing the heat indirectly. So the lines are blurred in some cases, but essentially the same concept holds, where you are extracting heat from the ground. In geoexchange, it is from a shallow depth, and for direct use, it's typically greater than 100 meters deep that you're dealing with. This slide here is showing an example where you're comparing what a conventional heating system using natural gas would give you, where 1 unit of natural gas would heat a home, and if you're using a pretty high efficient natural gas boiler at 90%, you're only losing 10% of that heat through that process. With geothermal heating, on the other hand, you do require electricity, but for that 1 unit of electricity, you can get up to 3 or 4 units of heat from the ground. And that's really important to hit home, because what essentially, when you're comparing then electricity baseboard heating to geothermal heating systems, you can really see the value of savings from that perspective. And in some cases, compared to natural gas, you do see some savings as well. So for geoexchange and direct use, the end use is very similar. So again, it depends on the temperature spectrum. So geothermal heat pumps can increase the efficiency of a geothermal fluid if the temperature of the fluids is not hot enough. So say something like less than 35 degrees Celsius. If you've got water at depth that's 60 or 70 degrees, then you don't need geothermal heat pumps, because the temperature of the waters are hot enough for the end use of that for certain applications. And if you've got temperatures that are 90 or 110 degrees, you're laughing, and you can utilize that fluid for several end-use applications in a cascading manner. So direct use applications in the US, and we're showing US as an example because they are definitely one of the leaders in the world using direct use. Direct use applications in the US have been growing at a rate of about 6% per year, and most of the systems are abundant throughout the western states. What's really interesting recently is that a hybrid system of both direct use and heat pumps can be used. So what that really means is that you might be drilling deeper into the ground to access aquifer waters, but then at the surface you're still using heat pumps, and you're basically increasing the efficiency of the system by doing that. So the difference between geoexchange and direct use is that heat pumps can essentially be used anywhere. You don't need anomalous heat areas to use heat pumps. You can do it anywhere. Whereas direct use applications, where you're looking for waters that are heated naturally within the earth, are more economically favorable in areas where known higher heat flow or geothermal gradient occurs. So although geothermal heat pumps was not a focus of our project, we would like to touch upon it a little bit just to show you how it works, because there's usually questions about how does a heat pump work? Is it geothermal? And yes, it is, and essentially it's just a mechanical system that transfers heat from a building to the ground heat exchanger or vice versa. And so what essentially that means is that it can be used for heating or cooling. The example that I'm going to go through to explain is a heating example, but you've got both the diagram here for a heating cycle and a cooling cycle. So essentially what happens is that water from a ground heat exchanger, and that could be a vertical borehole, or it could be loops that are buried under the ground, maybe 5 or 10 meters below the ground, or coils. So water from this ground heat exchanger circulates in the heat exchanger, where heat from the water is transferred to a low pressure refrigerant. And there are very many different types used. Essentially what it is it's a mixture of a vapor and a liquid. This refrigerant evaporates, and because it has a lower boiling point, it can do so at a lower temperature than water, which is why it's crucial that you use this secondary fluid. So this refrigerant evaporates in the heat exchanger and continues to a compressor, and this is where the electrical energy input is required to increase the pressure of the refrigerant, and that results in a temperature increase. This then high-pressure refrigerant vapor moves towards the heat exchanger, where the refrigerant heat is transferred to the air and distributed to a building in this case. The refrigerant condenses in a heat exchanger, goes through an expansion valve where the temperature is reduced and the pressure is also reduced. And then this low pressure refrigerant is returned to the refrigerant to water heat exchanger, and the cycle continues. So all that really means is that the heat is then exchanged from the refrigerant through that heat exchanger to the water that goes into the ground, and then the cycle just keeps continuing. And so this cycle is reversed when dealing in a cooling cycle. So we're also showing this diagram, which is a little bit easier to sort of envision what's going on with less of the detail involved. So what you've got is that you've got the heat coming from the ground through here, going through the heat exchanger. The heat is being transferred to the binary fluid or the refrigerant. This is where you've got your electricity input. The fluid, the refrigerant, increases in pressure, which raises the temperature. And that temperature is then transferred from the refrigerant to either a hot water system or to the air of a building. And then it continues on and it goes through an expansion valve where the pressure is reduced, thus lowering the temperature, and the cycle continues. So we've got a fun little video here to show what a geothermal heat pump is, and so it's a couple minutes long. I'm gonna just work this out and include it here, and then Kathy will take over after the video is complete.
We all want to save money heating and cooling our house or office, right? The answer may be under your feet, literally. Much of the heating and cooling can come from the ground, below the surface, with something called a geothermal heat pump. You see, below the frost line, about 10 feet down, the Earth maintains a nearly constant temperature of 54 degrees. We can tap into this energy to provide heating in the winter and cooling in the summer. Okay, now here's how it works. Bury a loop of pipes, called a heat exchanger, just below the surface, and fill them with water or a water and antifreeze solution. During the winter months, the air is usually cooler than the temperature below ground. The solution circulates in a loop underground and absorbs the Earth's heat. This heat is brought to the surface and transferred to a heat pump. The heat pump warms the air, and then your regular heating system warms the air some more to a comfortable temperature. Finally, ducts circulate the air to the various rooms. Now, a huge benefit is that the geothermal system doesn't have to work as hard to make people inside comfortably warm, and you save lots of money on your heating bill. In the summertime, the system works in reverse. When it's hot outside, the temperature below the surface is cooler than the summer heat. So, the fluid in the loop absorbs heat in the building and sends it underground. The ground's lower temperature cools it, and it's circulated again and again. Now you're saving money on air conditioning. Now, this church uses a large geothermal heat pump to heat and cool the building. It has a very big parking lot, which lets it spread out its loop horizontally. But if you don't have all that space, you can go straight down and use a vertical loop system instead. Geothermal heat pumps can be used just about anywhere in the US because all areas have nearly constant shallow ground temperatures, although systems in different locations will have varying degrees of efficiency and cost savings. The constant temperature of the Earth just below our feet is a sustainable resource, literally in our own backyard. It's a clean energy source ready for us to use, to heat and cool our homes and buildings while lowering our utility bills.
Welcome back. Now you've learned more about what geoexchange is, as well as more traditional geothermal energy extraction. So let's now talk about where is geothermal in British Columbia. This map was created as part of the project, and what it shows in all of the colors is where geothermal is in British Columbia. So there's a number of areas that are shown as stars, and these are areas which have already have surface manifestations. So we know that there is hot water in these particular spots. But around them are areas that also have potential, and those areas are shown in the pink and orange colors. So these are areas that have higher than normal or higher than average, what we call a geothermal gradient. And that means that the rocks, as we go downward, the rocks are hotter than what would be expected in other parts of the Earth. A standard geothermal gradient is shown in the blues and greens. So anywhere where it's elevated, there is the possibility of drilling down within economic distances, and those are maybe 1 kilometer, 2, 3 kilometers, and getting water that is sufficiently warm that it can be used for direct use, if not for power generation.
We've just been talking about where geothermal energy is likely to be found in British Columbia, but let's take a more global view. If we look at the Earth as a whole system, the Earth is split up into individual plates, and this process, these plates moving around, is called plate tectonics. The edges of these plates are areas with a lot of volcanism, and that's because at one edge, and those edges we call rifts or ridges, we're creating new crust. So in fact we have volcanoes which are erupting all along the mid-Atlantic ridge, for example, or out in the Pacific. So we have a continuous chain of volcanoes. Now for geothermal energy, what's important is when we're pulling apart the continent. For example, the East Africa Rift is an area of very high heat flow, lots of volcanoes, and also very prospective for geothermal on the African continent. In other areas, the plates are consumed, and we do that in a process which is called creation of the continental arc. And that is where the oceanic plate is crashing into a continental plate, and in doing so, one of the plates, the oceanic plate, is pushed down underneath and creates a line of volcanoes. And those line of volcanoes are called arcs. And we can do that either in the ocean or on the continent. But again, these are areas, and on the map, what you see is all the little tiny red triangles. These are areas where there's volcanic activity, and with volcanic activity we have heat because we're bringing magma close to the surface, and as a result of that heat close to the surface, there's a good possibility of creating geothermal systems.
So we looked at the map, our tectonic map that showed the crustal plates as well as all the volcanoes. So this is what it equates to in more a geological or geographical format. So you see large areas of blue. Russia doesn't have a lot of, except in the area of Kamchatka, and so you see a fairly low usage, or exploitation, we should say in this case. But in areas like the Philippines and Indonesia, there is a significant amount of power being generated, and that's because these are very volcanic areas. New Zealand as well has significant geothermal resources along the North Island. And I already mentioned the East Africa Rift Zone and Kenya being a very important in terms of the growth of the amount of geothermal power that's being produced. If we flip over to the northern hemisphere and the United States and Canada, what you see is Canada has no installed geothermal power, nor so no power generation is being carried out at the moment in Canada. But the United States has a significant amount, though most of that is centered around Nevada and California. California is where a lot of that video footage that you saw in the little video clip comes from, and that was the geysers area. But there were other photographs there that were from Nevada. Nevada is called a basin and range. It's an area of thin crust, and as a result, high heat flow. So I'm going to hand this over to Juliana for this part, and she's going to talk through the next several slides.
So in terms of where is geothermal for direct use globally, and what Canada's role is in that global growth, well, Canada is actually 5th already in direct utilization of geothermal by energy used. So there's various different ways that geothermal through direct utilization is measured, and one of those ways is energy used. And when using this measurement, Canada comes 5th. The really exciting thing is that there has been a 45% global growth since 2010, which is huge. And the installed capacity is about 70,000 megawatt thermal across 82 countries. And that's up from 48,500 megawatt thermal from 5 years ago. So this really shows you the increase in direct use, and that has helped offset almost 150 million tons of CO2 annually. And again, what's really important to point out here is that slightly more than half of this energy use is actually through geo-exchange systems. Other terms for these types of systems are ground source heat pump systems, ground coupled heat pump systems. There are various terms for it, which kind of confuses things globally in terms of what geothermal system is using geo-exchange. But the concept is the same. You're essentially extracting heat from shallow earth. And we'll be talking a little bit more about geo-exchange in Module 3. So this is a nice graph, although it's backwards. So basically, we're looking at growth from 1995 to 2015. Got 1995 on the right-hand side of the graph and 2015 on the left-hand side of the graph. So this is showing the direct use geothermal global growth over the past 20 years. And so in terms of direct use, including heat pumps, so you can see here that over 50% of geothermal direct use is heat pumps. And then the remaining of almost 50% is space heating, greenhouse heating, aquaculture, so that's fish farming, industrial uses, and bathing and swimming, which is spas essentially. So by far and wide, bathing and swimming is the highest after heat pumps, and then it's space heating, and then it's greenhouse heating, and then you've got pretty even between aquaculture and industrial uses. So if you exclude heat pumps from the picture, it does look a little bit different, but essentially it's the same pattern. Bathing and swimming is by far the most use for geothermal waters, and then space heating, etc. So this just gives you the picture a little bit more clear if you exclude geothermal heat pumps. So again, as I mentioned, Canada is 5th in direct utilization of geothermal by energy used. So how did this happen? Basically, we've got more than 140 thermal springs that are greater than 10 degrees Celsius identified in Western Canada. The First Nations were the first to use these resources for traditional uses such as bathing and cooking, and sacred uses as well. Banff National Park was the first national park in Canada, and it was created in 1885 as a result of a dispute about the right to develop hot springs. So there are 13 commercial hot springs in Canada. 9 of those are in BC, 2 in Alberta, 1 in the Yukon, and 1, surprisingly, from Saskatchewan. And this uses a water source from a deep, hot aquifer. So a great example of direct use that's drilling it a little bit deeper rather than, the easy hot springs that we have in BC that are closer to the surface. And basically that was just a failed oil well. So exploitation of shallow geothermal for geo-exchange is concentrated in Ontario and Quebec, but installations do occur across the country. And What we've got here is a statistic in terms of what the average unit is, and you've got the coefficient of performance, which is the COP, is about 3.5, which, if you remember one of the earlier slides, where we had 400% efficiency, this just means it's 350% efficiency. So for 1 unit of electrical input, you've got 3.5 units of heat being used from the ground. And 60% of those installations are residential. And one of the great, some of the great examples that we are going to be looking at later on in the case study module is that we do have some great examples of district energy geo-exchange systems in BC, one in Richmond, one at UBC Okanagan campus, and one in Gibsons, BC.
So now let's focus on where is geothermal in British Columbia. So I've already seen that heat flow map on the left-hand side, and you should remember that the pink areas are areas that have higher than average heat flow and thus are potential areas for direct use applications and in some cases power applications as well. And we also know that depending on the temperature, there's a very wide range of uses for that energy. Because even though we can't create electricity, we can actually use that heat more efficiently than for other uses, such as drying or bathing or space heating. There's been a number of maps of the geothermal potential in British Columbia that have been created over the years. These two, the one on the left was created by Ken Gia in 2014, and the one on the right by Steve Grasby in 2009. But they're all based on this map, which was created, or at least the British Columbia portions were based on this map, which was created in 1992. This was part of a large program run by the federal government, the Geological Survey of Canada, and part of that project was looking at where there are geothermal resources. So this map is a little bit different because it was done before we understood a lot about heat flow or had a lot of drill hole information about heat flow. And what you see in the pink areas was reflected in that earlier map of British Columbia, where you saw pink in there as well. And these are the areas that have good potential for geothermal because they are higher than average heat flows in most cases. Or there are volcanic areas, such as we see around Mount Garibaldi, down here in the south, or in the Stikine Belt up here in northwestern BC. So now you've had a pretty good flavor of the wide range of geothermal resources that are available, everything from power generation around our volcanic areas to geo-exchange, which is broadly applicable around the province. So why is it not more widely known, and particularly why is it not used? Well, part of it is a lack of awareness on what the lower temperature resource can be used for. So that's been the focus of our project, is trying to increase the awareness of what the geothermal is as a resource and how it can be used. Also, unlike a number of the other renewable energy, there are no government policies to make it competitive. And as a result, it has lagged behind things like wind and solar. And of course, here in British Columbia, we have inexpensive access to natural gas and also biomass for heating, as well as hydro for electricity. So with these cheap sources of power, which don't take into consideration the social and environmental impacts, geothermal production or geothermal development has waned. But we hope to change that in the coming decades because it's important. Local jobs, local economic development can be spurred on by a source of clean, low-cost energy, and that energy in the form of heat. So as the developments are worked on, we have things like local greenhouses, which can help with local food security. We have the production of breweries and using the heat in various aspects of that process. So these are entrepreneurial enterprises that can employ people locally. And of course, ecotourism is becoming increasingly important as a source of revenue for many small communities. And having a natural hot spring can be a major draw for tourists to an area. So in addition to all of these, we have many uses. So we're talking about heat from the ground used in heat applications. And also, in fact, that heat is a very efficient way to use the energy, because there's not that much that is lost in the energy conversion. It can be a very low-cost heat for space heating for businesses or communities. It can help eliminate greenhouse gas emission, can promote local food security through either food drying, greenhouses, basically growing more food close to the people who are going to be using it. And it's reliable. It's a proven technology, and it is sustainable in decades to potentially hundreds of years. So I'm going to let Juliana take over here, and what she's going to talk about is sort of the things that they're making the news lately in Canada in geothermal energy.
So over the next few slides, I'm going to take you through some examples of some of the larger grants that have been given for geothermal development research in Canada. And so I've left that statistic that Canada is the 5th largest producer of geothermal direct use in the world. We've got the hot spring resorts, of course. We do have some fish farms in the Yukon and BC. Geothermal cooling is used in tar manufacturing in Alberta. There's, for example, a community in Alberta that uses solar in a hybrid system with geothermal heat pumps. Essentially what happens there is that solar heat is stored in the ground from the excess heat in the summer, and then that excess heat is then used in the winter to heat the homes, it's won awards and it's quite an innovative system. Then we've got Manitoba, Ontario, and Quebec, which are leading the way in the largest deployment of geothermal heat pumps or geo-exchange systems. And in Nova Scotia, we've got the only example in Canada where an abandoned mine is being basically a flooded abandoned mine is used to heat a community because the waters in the mine are slightly elevated in temperature, and they can be used to heat some of the homes and buildings in the community. So one of the things that has really been gaining momentum lately is the fact that the oil and gas prices are low, and there's a huge amount of abandoned wells in Alberta and also in Northeast BC. So is there opportunity there to use the temperature and other geophysical property data that we know from drilling of these oil and gas wells? Can we use that data for geothermal and trying to evaluate what areas are the most favorable to use for geothermal? So again, I mentioned I was going to take you through some of the big grants that have been given in the last 5 or so years. This is an example of an almost $3 million grant that was given to a research institute in Quebec that is through the hydro arm of Quebec, kind of similar to BC Hydro, but the Quebec version of that. And so essentially what they're looking at is to study the potential for deep geothermal, that's enhanced geothermal systems for electricity production in Quebec and Atlantic Canada. And so that project is currently in progress, and will be really interesting to see how it moves forward. So we've also got this example of geothermal funding in Saskatchewan for a deep geothermal process where they're using information from oil and gas and knowing that there is a hot aquifer at depth, and that can be used for geothermal power production. And so the status of the project right now is that the demonstration project has been shown to be financially viable, and they are looking at funding to move forward and start drilling. And as I mentioned, in Alberta, they are looking at utilizing either abandoned wells for geothermal systems or re-drilling, in areas where they know that there is anomalous geothermal temperatures. And so we've got the Leduc Number 1 Energy Discovery Center, which is a museum just outside of Edmonton, Alberta. And this project, called the Living Energy Project, showcases geothermal for heating as well as wind and solar. And this is essentially being used as an educational moment for the museum, where they can show how conventional systems can be used with alternative energy technologies together to offset carbon emissions, for example. And so what's really interesting is that this project can be used as an example to convert other wells in Alberta that have been listed as inactive or abandoned, and how they could be converted to geothermal systems and put drilling and service companies back to work and use the heat from these wells for either microgeneration or to provide heat for greenhouses, things like that. And in BC, we have Borealis working with Casellas near Terrace in northwest BC. They got a $2.4 million grant from the Sustainable Development Technology Canada arm of the government. And so what they're looking at is developing an optimized geothermal exploration methodology, where if this methodology can be optimized and used for other geothermal systems in BC and the Yukon, other areas in Canada where there may be geothermal potential, it would allow for cost-effective exploration at a stage where it is very, very expensive and a high risk of drilling basically a dry well. So if you can optimize that process to minimize that risk, that is very beneficial for developers and explorationists. So, just bringing this slide back to, again, showcase that geothermal is a spectrum, and it depends on the temperature of your fluids. The higher the temperature, the more you're able to use it for power. And then the mid-range, you can use it for processes that require higher heat, so like industrial processes. And then at the lower range, you can use it for heating spaces like greenhouses or aquaculture, fish farming, residential, commercial areas.